So in the first lesson, what we did is we're looking at variables in general. Okay, so the thing that I wanted to focus on in that lesson is to get you to understand some of the main things about the ways in which we can measure things. So it's one of the most important things they teach you at the very start of physics is how you can measure things and what different types of measurements there are. So we looked at some examples of quantities that can be measured, as in they would have a numerical value. Okay, technically a color, when you write down the color of something, that's a measurement, but it's not a number. So we're talking about numerical measurements. These are some examples, and I did some symbols of each one as well. I then we came up with a SI unit, and SI it's a French word, Systems International or International. Obviously, my French accent's awful, but it's the standard unit for that particular measurement. Okay, so speed. The standard measurement is meters per second. The standard measurement for force is newtons, and so on. That's the SI unit. Now, there's obviously loads of other units for speed. For example, we know kilometers per hour, miles per hour. Knots is a unit that you measure the speed of boats. And anyway, but these are the standard units that you would use. Now, the standard units, the reason why standard units are important is because they can be interchangeable. When you use these equations, for example, a very good example, I think, is F is equal to ma, so that the force is equal to mass times acceleration. Force is in newtons. If I didn't have these in SI units, the equation just wouldn't work. You'd end up with something with the wrong answer. So you have to have them in SI units for it to work most of the time. So that's the SI unit, and this is the symbol for the SI unit. So you've got the symbol for the actual quantity, then you've got the symbol for the unit. And then we talked about scalars and vectors. So this led in nicely into the difference between scalars and vectors. The main difference was that they're both quantities that you can measure in both cases. They both have a size or magnitude, but only a vector has a direction. So if I tell you that a force is acting and the size of the force is 5 newtons, and I ask you to explain what's going to happen, you're not going to be able to tell me unless I tell you what direction the force is acting on. So what force the direction is acting in. So direction is important for vectors. So these are some examples of scalars and vectors. We did a little explanation about how we can add vectors to find resultant vectors, and this was a story of a guy leaving home, going 5 meters east, and 10 meters north, 10 meters west, 2 meters south, and then 3 meters east. And what we were doing is we were working out the resultant displacement. Displacement is a vector, and distance would be a scalar. So I asked you to work out what the total distance was and what the total displacement was. The total distance would be 30 meters, and to work out the total displacement, we would actually measure the distance from here to here once you've drawn it out. So the distance is just how many meters he's traveled. If he was using a mileometer on his car, the mileometer measured the distance. Whereas if you want to know how far you have got from your home, like how far is home currently away from you, then now you're talking displacement, because to work out all that, then you would need you would need a direction. So what I then said is that you can actually use the same approach with adding all vectors. So if this wasn't displacements, if this was forces, it's like a 5 newtons to east, 10 newtons north, 10 newtons west, and so on. To add up all those vectors, we would do exactly the same method, and the resultant force would be that size and that direction. So although adding forces is a little bit weird in that way, the same would apply. Now we can look at some simple example there. So we'll just let's start off with something that we already know the answer to. So if we get a force pulling this way of 5 newtons and a force pulling this way of 5 newtons, well, we know the resultant force is 0. We can see that, and we've learned that from GCSE and also Key Stage 3. But in terms of A level, the way you want to do it is imagine the same way of this man walking around. We would go start 5 to the east, and then go 5 back to the west. And how far has he travelled? 0. So the answer is 0. So the reason we have to use this A-level approach is when we end up with situations where they don't cancel out and they end up in different directions. So let's say if we had 5 newtons up there and 5 newtons here. If this was displacement, we would go 5 meters to the right and 5 meters up. What's the total displacement? Well, it's from here to, oops, it's not very accurate, from there to there. So that would be the resultant displacement. And because we add them in exactly the same way, it's also the resultant force. So that's what now I won't go into how we do that, but I'll briefly just say it's Pythagoras, and I'll leave it at that to calculate that. So that's what we did in terms of quantity. So that's the summary video for that one.